So in this video, we're going to go through two of our most fundamental objects in 3 dimensions, and those are going to be talking about lines and then talking about planes. And by planes, we mean something other than our coordinate planes, because those are pretty easy to describe just by setting one of the components equal to 0, and then the other two variables can be free. So what happens then if our plane is at some angle instead? So we're going to begin by going through lines first, though. And the way we're going to actually introduce these is through a concept called vector valued functions. So we're going to begin with that. So a vector valued function specifically, we're going to just kind of talk in R2 for right now. Or you can simplify this as a vector function. In R2, or similarly in R3. Is really a function of a specific form. So it is a function of the form R of t. So t is going to be the thing that you input. We use r to indicate that this is that vector function with that arrow above it. And the output of this is going to be a vector for each t value that you input. Okay. So in R2, it's just going to have the two components, and it's going to give you a two-dimensional vector. And this value of t is just some real number. Right? So technically, it's a single valued function because you're only inputting t. The output, however, instead of it being like just a y value, it's going to give you an xy coordinate. So what you can kind of think of is this is really kind of like parametric equations, if you remember doing those in Calc 2. So each parameter t gives you a vector, and the end of that vector is going to be the curve that's traced out. So really, we can think of vector functions as a system of parametric equations with parameter t. So to give you a visual of this, we'll do again 2 dimensions. Suppose here is our xy axis. And let's say you input one value of t, and it gives you this vector. So just starting at the origin. You input another value of t, and maybe it gives you this vector. Input another, it gives you this. So what happens is your curve is actually going to be traced out by the endpoints of these vectors. So our function r of t might look something like this, and it's being traced out in this directions as you increase that t value. So here is r of t. Okay. So same exact kind of concept. It does have a direction. You can kind of come up with the same vector value function in the opposite direction to just trace it out the opposite way. Right now, orientation doesn't matter too much, but again, when we start talking about vector calculus, the way in which the curve is traced out is going to be important. Okay? So now we have a little bit of idea about this. Again, you can go back and review your Calc 2 stuff if you need some familiarity with your parametric equations. But we're going to work now specifically with lines and then planes. So if you think back to 2 dimensions, because again, we kind of want to do natural extensions for a lot of these shapes. In 2 dimension, we know the equation of a line through 2 things. We needed the point the line passes through, or any point, and then we need the slope of a line. So we know the equation of the line by knowing the slope and a point on the line. Okay. So in our visual of that, here is our XY plane. You know a point that the line passes through, say x naught, y naught, and then you know the slope, which gave you the rise over run, and it told you basically another point on the line here. So this would be the equation y equals mx plus b. M is that slope, or in point slope form, remember this is y minus the y coordinate is equal to the slope times x minus the x coordinate. So this is going to have a very natural extension, because if we're working in 3-dimension, I really just need to know the same thing. I need to know a point that the line passes through, and I need to know which direction it's headed. Here, you only had technically 2 directions. You needed to know the rise and the run. So in 3 dimensions, I basically need to know what's happening in each component instead. So in R3, we can determine a line L by knowing a point, which in this case I'm going to call P, and we'll call it P0 to indicate the initial. So it has coordinates x naught, y naught, z naught. So we can determine a line L by knowing a point on the line and the direction of the line. So the direction is essentially what that rise over run is, but in each of our different components. So the direction of the line is described by a vector v that's parallel to our line. So again, give you a visual before we start doing the nitty-gritty details of it. So here is our 3 dimensions. We've got the x, y, and z axes. And then when you talk about a line in space, it's the same thing. Here maybe is the point P naught that this line passes through. And then it just has that straight shape to it. So maybe this is our line L. Okay. So all I need to define this line is this point, and I need to know the direction that vector or that line is heading just by having some parallel vector v. So it's heading in exactly the same way as the line. Right? So let's see if we can determine what the equation is going to look like knowing these 2 things. If I have this initial point and I have my direction vector, what should the vector function be that describes this line L? Right? So we'll try to take that piece by piece and go relatively slow for it. So if we want to determine the equation of the line, we're going to let P, which will have coordinates x, y, and z, be any point on the line L. And then we're going to define the vector r0 to be the position vector of this. Okay. So we let R0 be the position vector. And then we have this point B, which is P, which is any point on the line. So we're going to let R be the position vector of P. Okay. So let's go through the visual of what we have going on here. I'm going to make this a little big because we're going to need to draw lots in here. So here is our X, Y, and Z axes. So again, here is this line that I'm trying to find the equation of, and I have this point that I know the line passes through, which is P naught, and it has coordinates X naught, Y naught, Z naught. Okay. Then I also know this direction vector B, so that passes through the origin and it runs parallel to L. Okay. So the vector R naught is defined by going through the origin, and its endpoint is going to be at P naught. So this is R naught here. And then my point P is any arbitrary point along here. So I don't know the coordinates. It's some X, Y, and Z values on the line. So R is the position vector for this. And my goal is to figure out what is R. What does this equal? Okay, because that is going to be my vector function. This is any point on the line. So it's giving me how do I figure out the X, Y, and Z coordinates for that point. Okay. So what I'm going to do is I'm going to define this vector connecting R2 to be A. I don't know what that looks like right now. But however, because I have this triangle in here, remember our sum is if I add these two together, it gives me that resultant diagonal. So what I'm actually able to say then is that my vector R is going to be the sum of R naught plus A. Okay. And so I'm getting somewhere. My goal is to figure out what is R equal to. But again, I have no idea what this vector A looks like. I do know what R naught is because it's just the point X naught, Y naught, Z naught in vector form. However, because this vector is on my line, I know it runs parallel to my vector V. So vector A is some scalar multiple of V. So since A and V are parallel, I know that vector A is some scalar multiple of V. And that scalar that I'm going to use is T because I have no idea how much I shrunk V by or how much I extended V by. Because again, P is some arbitrary point. So it could be my point is all the way back here and my vector A is going to be super long. It could be that my vector P, if this thing continued, is all the way out here and I have to stretch it by a lot. Okay, so it's some arbitrary multiple of V. So what I can utilize, I know my vector V, I know my vector R naught. T is the parameter that I'm searching for to scale this up or down. So ultimately what I get is the vector R is equal to that initial position vector plus some scaled version of that direction vector V. So this is the vector function of line L. So you're probably still asking, okay, well, what then does the actual equation look like? So let's get into the formal definition of it. And hopefully you'll see that it is, again, a really natural extension to our normal equation of a line. So if we know the direction vector v has the components a, b, c, then t times v is just going to be each of these numbers scaled by t. So letting the vector r have the components x, y, and z, because again, that is that position vector here. You just turn this into a vector instead. And then knowing our initial position vector has the coordinates x naught, y naught, z naught. Then more formally, our vector function r of t is going to be given by, you do x naught plus tv. So that first component is x naught plus t times the direction we're heading in the x component. So really, this is exactly like y equals mx plus b. This is the value of b, and this is that slope, and t is the variable. And then likewise, you do exactly the same thing in the other components. It's that initial value plus the direction you're heading in the y component times that parameter t. And then here, it's z naught plus c times t. And then your t is just a real number, and again, it lets you just draw the shape out, okay? So just kind of matching up all these pieces, so you see r naught is exactly those initial components. The parameter t is attached in each of these, and then v is exactly a, b, c. Okay? So this is our vector equation for a line in 3 dimensions. Now from here, you have a couple other things that we can kind of define. Some of them are just terminology. So the first one is going to be the parametric equations from this. So the parametric equations of a line. Are the following. Our x-coordinate is given by x naught plus at. The y-coordinate is given by y naught plus bt. And the z-coordinate is z naught plus ct. And then those three are grouped together, and the value of t is going to vary. Okay. Then also, in a similar manner, you have something called the symmetric equations. So these aren't as important that you need to know. Typically, we're just going to use the vector function or the parametric equations themselves. But this is something that can pop up. So the symmetric equations are the following. It's really just a rearrangement of each of these. So what you do is you subtract the x-coordinate, divide by that slope here. And that gives you a way to represent the parameter t. But in doing so, this is the same t in each of these. So you get 3 different kind of expressions that are all equal to each other because it's the same t. So from the first one, we're going to take x, we subtract the x-coordinate, and then we divide by a, and that gives us the value of t. It's kind of like when you eliminate the parameter. But then doing the same thing and solving for t here gives you y minus y naught over b. And then likewise, if you solve for t here, that would be z minus z naught over c. Because all of these represent that parameter t, we just say these are all equal to each other. So it gives you a set of symmetric equations. Okay? All right, so now that we've got that down, let's try an example before we get to planes. You'll have lots of examples in your homework. So let's find an equation of the line. Passing through the points 1, 2, 1 and 3, 0, -1. So we're going to come up with that vector function to find this, but then also in addition, we're going to find the symmetric equations. But once you have the equation of the line, not too hard to figure out what the symmetric equations are. Okay? You have a bunch of different ways to do this. You have technically 2 points here, which is great because I can use either one of those to come up with the equation of my line. However, the thing I'm missing is the direction of this line. But remember, if you were given 2 points, you could figure out everything you needed to find the equation in 2 dimensions, because all you had to do was find the slope between those 2 points. So for this case, it really makes no difference which one you pick to be the initial point. I'm going to go ahead and say this is our initial point. But you would get something very similar if you used 3, 0, -1. It just might be traced out in a different direction. Totally fine. Again, you get the same exact thing. But for our purposes, let's just do the first one for the initial point. So let's make 1, 2, 1 the initial point. Okay. Now I need the direction this line is headed. But since I have those 2 points, we just take the difference of them. So let's call this point A and this point B. Okay. Then the direction vector of this line is V, which is from A to B. So all you do is take one point and you subtract the other. So in our x-coordinate, that will be 3 minus 1. In the y, it's 0 minus 2. And in the z, -1 minus 1. So going through this subtraction, our direction vector is 2, -2, -2. If you did the opposite and you made this your initial point and you subtracted this one, all it would give you is the same exact vector, but opposite direction. So you trace out your line in a different, in the opposite direction. Okay? So I have the 2 things I need. I have my initial point. I have this direction vector. So we can immediately say now what the vector function is. So we have our vector function r of t, and it's going to have 3 components. So in that first component, it is the initial point plus the direction we're heading in the x. So here it's the initial point plus the slope in the x direction times t. Okay. Then for our second component, it deals with 2 and -2. So our initial y value is 2, our slope is -2, and then our parameter is t. And then finally, in the z component, our initial value is 1, the slope is -2, and that gets attached to the parameter t. And then our value of t is any real number to allow the entire thing to be traced out. Okay? So that is our vector function. And now from here, I can say the symmetric equations are the following. So we do x minus the x coordinate of the initial point, which is 1, looking at the wrong thing. So it's 1, and then our slope in the x direction is 2. So we divide this by 2. For our y symmetric equation, the initial point for y is 2, and the slope is negative 2. And for z, the initial point is 1, and the slope is negative 2. So these are the symmetric equations. Again, if you use this point as the initial one instead of 1, 2, 1, you'd end up with something very similar because your direction vector would just have been the opposite, and it'll all work out. The same solutions or the same x, y, and z values that satisfy this would also satisfy the other equation. Okay? Now I am going to make one note here for this vector function because very soon in the future we're going to have to talk about coming up with an equation to describe a surface. And so what I want to do is just show you something nice that happens as a result of this. So notice if I plug 0 in for t, then that's going to give me 1 plus 0, which is 1, 2 minus 0, which is 2, and then 1 minus 0, which is 1. So this is exactly the initial point. The end of this is the initial point A. And then if I plug in 1, that's going to give me 1 plus 2. Then it'll give me 2 minus 2 and 1 minus 2, which is exactly 3, 0, negative 1. So this is the second point that I used. I'll call it essentially the terminal point, B. So what I can do if I don't want the entire line formed, restricting my t value to be between 0 and 1 is giving me the line segment between these 2 points. So here, restricting t to be in the interval 0 to 1 gives us the line segment between point A and B. Because again, very soon we're going to have to talk about optimization. We're going to talk about absolute maxes and mins, and we're going to be concerned with on a specific border, which could be a straight line. So I have to talk about just restricting it to this particular portion of a line. So let's move on now and let's talk about planes in 3D, because those are going to be a little bit different in terms of what that equation looks like and what we need to come up with the equation. So a plane in space is definitely more difficult to describe than a line. So in this case, we're going to need a point that the plane passes through, but a single vector parallel to the plane is not going to be enough information for us. So just knowing a vector that's parallel is not enough information, because technically there's a ton of vectors that are parallel that those vectors themselves are not parallel to each other. And that seems like a really weird statement, so I think I'll just draw you a little picture. So here's our plane. This is the thing I'm trying to find the equation of. I have one vector here This is technically parallel to the plane if it lies in it. But I have another vector going this way that is also parallel to the plane, but it's not parallel to this vector. So just a single vector like that is not enough information for us to come up with the equation. So instead, I still am only going to need two pieces of information. I need a point that the plane passes through, and I'm going to actually need a vector that's orthogonal to the plane. So although one parallel will not be enough information, switch back to the right color. However, a vector orthogonal to the plane is enough. So we know orthogonal means perpendicular. It gets another new name right here. This orthogonal vector is called a normal vector. So third name meaning the same thing. Perpendicular, orthogonal, normal, all describe that it's going to meet whatever object that is at a right angle. So let's go through our formal definition for the plane. We're going to let P naught be that point on the plane. So it has the coordinates x naught, y naught, z naught. We're going to let this be a point. And instead of using a vector v to describe that direction, we want an orthogonal vector or a normal vector. We're going to call that n. So we're going to typically use n to describe normal. We're going to say this normal vector has components a, b, and c. And specifically, we do need this to be a non-zero vector. Otherwise, that would be a very boring plane. Okay. The way we're actually going to describe the plane is by picking all points so that the vector between x naught, y naught, z naught, and this arbitrary point P will be orthogonal to the normal vector. So let's go through that phrase and then draw a picture here. So the set of all points P, which we have no idea what the components are, so we'll call them x, y, and z, such that the vector P0P is orthogonal to n, is called a plane. So let's go ahead and draw our picture. So here is our plane, hanging at whatever angle you want. Here is this point. Actually, let's make this a little bit bigger. There's a nicer looking plane. Here is the point P0, which has the coordinates x0, y0, z0. Our normal vector n is going to be orthogonal to this plane. So it's going to shoot directly off. So here is n, which has the components a, b, c. What I want to do is I want to find all of the points so that when I draw the vector out to here, this vector forms a right angle with my normal vector. This vector here forms a right angle with my normal vector. So the endpoint of each of these is P, which has arbitrary coordinates x, y, z. And same thing, if I were to draw the vector back here, it's going to form a right angle with that normal vector. Okay. So knowing this is how a plane is going to be defined, I can actually come up with the equation. again, this and the initial point are potentially given to us, but it's something that I can find and I know. So from that, what I'm going to do is I'm going to figure out what is this vector here, which is exactly P0 to P. So notice P0P is just the difference between those 2 points. So it's x minus x naught, y minus y naught, z minus z naught. Just the difference in the x, y, and z coordinates. Because I know this vector is orthogonal with n, we know that the dot product between those two vectors has to equal 0. Because if the dot product is 0, we know those two vectors are perpendicular or orthogonal. So from that, since P0P is orthogonal to n, we have that when I take the dot product of P0P and n, we'll put n in the front, we know that's going to equal 0. But I know what the components of each of these vectors look like. So really, n has the components a, b, and z. And then P0P is x minus x naught, y minus y naught, z minus z naught. So if I do the dot product, we just multiply the like components and add. So for the first one, we have a times x minus x0. Then we add, doing the same thing to the second component. Oh, that's both of them. So we add b times y minus y0. And then doing the same thing to that last component, we add c times z minus z0. So this is the equation of our plane. If you left it here on a test, perfectly fine. If you're asked to come up with the equation of the line, absolutely leave it like this. What you might have to do in your homework, so be careful, especially on the web assigned components of your exam, you've got to possibly put this thing in standard form. And so what that means is we really don't like all of these different constants together, so we kind of group everything. So what happens is if you distribute this constant out, what that would end up with is a times x0. That's going to be some number. You'll have b times y0, also a number. C times z0, also a number. And then you'll just have that a, b, and c attached to the x, y, and z. So if you just rearrange that slightly, if you move everything dealing with the constants by adding them over to this side, it will give you a times x plus b times y plus c times z over here. So again, distributing that out leaves this over here, and then adding the ax0 gives you what you get on that side. Okay. All right, let's get rid of all of these. But realistically then over here, these are all constants. So instead of writing all of that out, we'll just rename it to D. Okay. So this format here is the standard form of a plane. So this one, fine on a test, but this one is the standard form of a plane. Okay. So let me do an example just to show you Again, if the directions don't say to put in standard form, you don't have to go through this rearrangement. We'll do a nice example and then we'll do a harder one from there. So let's find an equation of the plane. Through the point 5, 3, 5 with normal vector two, 1, -1. So you don't need to do this first step. I'm going to do it again just to show you, because this is our normal vector n. If I go ahead and I dot product this vector with x minus my initial point, y minus my initial point, z minus my initial point, this thing should equal 0. Okay. So going through that, that will give us 2 times x minus 5 plus 1 times y minus 3 minus 1 times z minus 5 equals 0. Okay. This is the part perfectly fine on your test. I don't need you to distribute this out and rearrange some algebra. So on any written portion, if I ask you to find the equation of a plane, this is good. But if it does say put in standard form, especially in your homework, you do have to go through and rearrange this. So all that means is let's distribute all of these out. So that's 2x minus 10 plus y minus 3 minus z plus 5 is 0. Combining the like pieces, minus 10 minus 3 plus 5 will give us a -8. So that's 2x plus y minus z minus 8 is 0. And then you just move the constant to the other side. So this would be standard form. Okay. So hopefully not too terrible. Okay. Let's do one more example. And instead of knowing the normal vector, instead I'm just going to know 3 different points that the plane is going to pass through. So in that case, I know a point, but I don't know the normal, so I have to find that first. All right, so for our last example on planes, we're going to find an equation of the plane. That passes through the points P, which has coordinates 0, 1, 1, Q, which has coordinates 1, 0, 1, and R, which is 1, 1, 0. So I definitely don't want to graph these points and try to draw the plane that it looks through. So a lot of times what you're going to see is just kind of like a mock-up of what this does potentially look like. So although I don't know the plane, we'll draw what a plane looks like, a just flat sheet. I do know it passes through the points P, Q, and R within here. So what I need to do is I need to find the normal vector. But because it contains these points, that means it contains the vector PQ. And it also contains the vector PR. Okay? So PQ and PR are vectors in the plane. So if I'm looking for a normal vector, I'm looking for one that is orthogonal to every other vector you create in the plane, well, I know if I take the cross product of these two vectors, it's going to be orthogonal to both of them. So what I can do to figure out my normal vector is figure out what is PQ cross PR. Okay. So since those are two vectors in the plane, the vector PQ cross PR will be normal to the plane. So I need to find the cross product. I got to figure out first what is PQ and what is PR, but that thankfully is not too terrible. So PQ, we look at the difference in components. So that's 1 minus 0, 0 minus 1, 1 minus 1. So my vector PQ is going to be 1, negative 1, 0. And then for the vector PR, I look at these 2 points now. So in my x component, that's going to be 1 minus 0. My y is 1 minus 1. And my z is 0 minus 1. So PR is the vector 1, 0, negative 1. So now we go ahead and we take the cross product of these two. So we start by doing our I, J, K. Makes zero difference which one you pick to be first, because again, remember, they're just going to point in opposite directions. Still going to give you the same information. So I'll put the first vector, which I put PQ, and then we put PR here. So going through our determinant here, I'm going to reduce it to my smaller determinants of 2 by 2. So we've got positive I, negative J, and then positive K. So for the first one, we strike out first row and first column, and what's left is negative 1, 0, 0, negative 1. First row is always going to be struck out, so just keep moving. Then for our second matrix, strike out the middle column, so that leaves us with 1, 0, 1, negative 1. And then finally, strike this one out, and that leaves us with 1, negative 1, 1, 0. Okay. So at this point, I don't need to keep doing I, J, and K. So for our first component, we multiply, that's positive 1, subtract 0. So if the first one is 1. The second component is negative, and then we go ahead, multiply, that's negative 1, subtract 0. So it's really negative, negative 1 in that middle component. And then finally, we have 0 minus negative 1. So the last component is positive 1. So this works out very, very nicely that the vector 1, 1, 1 is what's orthogonal for us. So here, n is the vector 1, 1, 1. So we have a normal vector. We have 3 different points that this plane passes through. So again, use either one of these 3. It will get you to the same thing. It is always natural to just use this first point here. So n is a vector that's orthogonal to the plane, a point it passes through. just to have it down in the same area, is P, which is 0, 1, 1. Okay? So the equation of the plane is the following. At this point, I won't do that dot product. Our normal vector is 1 times x minus the x coordinate of the point, plus the middle component of the normal vector times y minus the y coordinate of the point, and then z times z minus the z coordinate of the point. Again, if you left it here, perfectly fine, makes no difference, but just to show you standard form, that gives us x plus y minus 1 plus z minus 1 equals 0. And then rearranging this just gives us x plus y plus z. That's minus 2. So really you end up with plus 2 over here. And just to show you, if you picked a different point, say you picked Q, which has the coordinates 1, 0, 1, all that does is it shifts things around. So it's x minus the x coordinate, y minus the y coordinate, and z minus the z coordinate. So it really ends up with exactly the same thing because you have x plus y plus z and the minus 2. So pick any point you want. You can pick the simplest, especially if stuff has 0 in it. Great. Totally up to you.